For centuries, humanity has looked up at the night sky, filled with questions regarding the mysteries of the universe. During the 20th century, scientists introduced the theory we now refer to as the Big Bang Theory. However, this theory has struggled to address essential questions about the universe's origin, its development, and its continuous expansion. More recently, new research has complicated this enigma even further. In 2023, NASA's James Webb Telescope made a groundbreaking discovery, detecting celestial objects that appeared to be older than the universe itself. This revelation has left researchers astounded, raising doubts about whether a star could possibly exist for a time exceeding that of the universe. This new discovery has sparked serious reflection about our current understanding of the cosmos, suggesting that perhaps a new model is needed to make sense of these mysteries. These questions and many others will be explored in this video. If you're interested in staying informed about the latest developments in cosmic news, make sure to subscribe to our channel, like the video, and hit the notification bell. Approximately 200 light-years away from us, in the coastal region of Esli, lies an ancient star identified as HD 14283. The remarkable speed of this star, traveling at an astonishing 44.83 kilometers per second, provides important insights into its dramatic history. About 1 billion years ago, during a time when our own Milky Way galaxy was still forming, it collided with a smaller galaxy, which is where this star originally hailed from. However, what makes HD 14283 even more extraordinary is not its velocity but its immense age. The star is considered one of the oldest celestial bodies that we have ever had the chance to observe, earning it the nickname Methuselah, a reference to the biblical figure said to have lived for 969 years. Initially, scientists believed it was roughly 16 billion years old, but further estimates suggest it may be around 14.46 billion years old, with a margin of error of about 800 million years. This discrepancy presents a serious paradox, especially when compared to the universe's age, which is estimated at approximately 13.8 billion years, based on observations of the cosmic microwave background. The big question now is, how can a star be older than the universe itself? This apparent contradiction has led scientists to question the accuracy of their dating methods and, ultimately, the true age of the universe, prompting further exploration of these profound cosmic mysteries. To properly investigate this, it's essential to understand that calculating the age of celestial objects is an extremely complex task. Stars like our Sun maintain their temperature and size relatively unchanged for billions of years, which makes estimating their age particularly challenging. Astronomers observe small variations in the brightness and color of stars over time, and use these measurements in conjunction with mathematical models that predict the evolution of stars. One crucial indicator for estimating a star's age is its rotation rate. Stars slow down over time, much like a wheel gradually losing speed due to friction. By comparing the rotation rates of stars at different ages, astronomers have established mathematical models that allow them to estimate the age of a star using a method called gyrochronology. Methuselah, as one of the oldest stars we can study, offers a relatively accurate age estimate. Instead of focusing solely on whether it might be 2 billion years older than its counterparts, we could approach this from a new angle. Could it be that the universe is much older than scientists initially believed? Understanding the vastness of 13.8 billion years is a challenge. To illustrate, imagine compressing the entire history of the universe into a cosmic calendar. In this analogy, the Big Bang would be akin to the most spectacular fireworks display on New Year's Eve, while Earth would only emerge towards the end of the year. Human history on this scale would barely cover the last 10 seconds of December 31st. To determine the age of the universe, scientists study light from stars that formed hundreds of millions of years after the Big Bang, using the phenomenon of redshift. As the universe expands, light from distant stars stretches into longer wavelengths, known as redshift. By analyzing both the observable distances to galaxies and the rate of cosmic expansion, scientists have deduced that the universe is approximately 13.8 billion years old. However, recent findings from researchers at the University of Ottawa have suggested that the universe may actually be much older, around 26.7 billion years. Professor Rendra Gupta, a physicist from Ottawa, has proposed a theory that combines Swiss astronomer Fritz Zwicky's 1920s ideas with newer concepts. Gupta's theory posits that protons lose energy over vast distances and times, which could alter our understanding of the redshift phenomenon. Although this idea contradicts certain observable data regarding redshift, Gupta suggests that we could reinterpret it as a hybrid phenomenon, partly caused by the universe's expansion and partly by these proton energy losses. If this hypothesis holds true, it would significantly increase the estimated age of the universe and could provide new explanations for long-standing cosmological questions, as well as new puzzles raised by NASA's recent findings. The James Webb Space Telescope has been key in arriving at this revised estimate of 26.7 billion years. Gupta's theory incorporates the tired light hypothesis, which proposes that light from distant stars may lose energy as it travels through space, and combines it with Paul Dirac concept of evolutionary interaction constants. This suggests that interactions between fundamental particles might evolve over time. Interestingly, this wouldn't be the first time that the age of the universe has been revised. In the 1920s, astronomer Edwin Hubble argued that the universe was only 2 billion years old. Over the decades, our understanding has improved, and the estimated age of the universe has more than doubled. This progress represents a crucial step forward as astronomers refine their models of cosmic history. Regardless of whether we consider human history to be equivalent to just a few seconds in this vast cosmic timeline, one thing remains certain: the universe is incredibly old and awe-inspiring. Its continuous expansion challenges our previous notions about its age, but there are also striking observations related to our own galaxy, the Milky Way. Recent data suggest that stars in the outer regions of our galaxy are moving significantly slower compared to stars in similar positions in other galaxies. This phenomenon presents two possible explanations. One is that our galaxy contains a particularly small amount of dark matter, an invisible substance that plays a key role in the gravitational interactions between cosmic objects. The other possibility is that our current understanding of dark matter, its distribution, and abundance might be far off from reality. This dilemma arose from data gathered by the European Space Agency's Gaia satellite, which provides detailed measurements of the positions of nearly 2 billion stars in our galaxy. These findings have prompted astronomers to rethink their models of stellar behavior, especially when it comes to stars at the outer edges of the Milky Way. The speed at which stars move is an important factor in estimating the mass of a galaxy, as the gravitational force acting on each star depends on the total mass of the galaxy. A recent study, based on Gaia's data, calculated that the total mass of the Milky Way, including gas, dust, stars, and dark matter, sits at roughly 200,000 billion times the mass of our Sun. While this estimate is still significant, it's about 5 times smaller than earlier calculations. This discrepancy could indicate that there's less dark matter in our galaxy than previously thought. However, measuring the mass of a galaxy is an inherently difficult task, so there may be some uncertainties in the data provided by Gaia or the methods used to analyze it. We continue to stay updated with new discoveries in this field. If you enjoyed this video, please like and subscribe, and we look forward to sharing more updates in the future. As we look further into the complexities of these findings, it's important to consider that space exploration and cosmic observation are evolving fields, and with each breakthrough, our comprehension of the universe deepens. The discovery of unexpected cosmic phenomena, such as stars potentially older than the universe itself, forces us to confront limitations in our current theories. This ongoing journey invites a reevaluation of fundamental concepts in physics and astronomy, challenging us to keep refining and expanding our understanding. In addition to these revelations, astronomers and physicists are also investigating other aspects of cosmic structure and behavior, such as the distribution and behavior of dark matter. Dark matter, which cannot be directly observed, is thought to constitute a significant portion of the mass in the universe. Its elusive nature has sparked numerous theories, each of which carries different implications for the structure and formation of galaxies. Some scientists speculate that the absence or reduced presence of dark matter in certain regions of space could help explain unexpected observations, like the slower movement of stars in the outer parts of the Milky Way. The intricacies of these studies are made even more complex by the fact that much of our current data is based on indirect observations. Instruments like the Gaia satellite provide precise measurements, but interpreting these data is fraught with challenges. The position and movement of stars, especially in outer galactic regions, are affected by a wide range of factors, making it difficult to isolate the causes of observed behaviors. As researchers continue to gather and analyze more data, we may uncover new patterns that could shift our understanding of galactic evolution. One of the most exciting prospects of this ongoing research is the potential for a paradigm shift in our conception of the universe's age and structure. If the theories proposed by Gupta and others hold any weight, it could revolutionize our understanding of the cosmos, placing the universe's true age much older than we previously thought. The implications of such a shift are profound, potentially altering our view on the nature of space-time, the laws of physics, and the history of cosmic events. Additionally, advances in observational technology, such as the James Webb Space Telescope, allow us to peer further into the past, examining distant stars, galaxies, and cosmic phenomena with unprecedented clarity. These advancements are opening new frontiers in space exploration and pushing the boundaries of what we know about the universe. The possibility of discovering ancient celestial objects that challenge our existing models is an exciting prospect that continues to inspire curiosity among scientists and enthusiasts alike. The debate over the true age of the universe also prompts broader questions about the nature of scientific inquiry itself. How do we reconcile contradictory data? How do we adjust our models in the face of unexpected discoveries? The pursuit of knowledge in cosmology is an ever-evolving endeavor, and the discoveries made by NASA, the University of Ottawa, and others highlight the dynamic nature of scientific exploration. Each new finding not only adds to the mystery, but also brings us closer to unraveling the truths that govern the universe. As we continue to explore these questions, it's essential to remain open to new possibilities. The universe, with all its vastness and complexity, might hold answers that we haven't yet imagined. Perhaps the real mystery lies not in the stars themselves, but in how we interpret the data and theories that emerge as we push the boundaries of knowledge. The future of cosmology holds great promise, and as we unlock new layers of understanding, we will inevitably gain more insight into the true nature of the universe. In conclusion, while the questions surrounding the age of the universe and the existence of ancient stars present intriguing puzzles, they also offer us an exciting opportunity to expand our comprehension of the cosmos. We must continue to question, explore, and refine our models of the universe as new discoveries emerge. Whether the universe is 13.8 billion years old or potentially older, each new discovery adds a piece to the puzzle, guiding us toward a deeper and more profound understanding of the universe's origin, structure, and future. Stay tuned for more exciting revelations as scientists around the world work tirelessly to uncover the mysteries of our vast universe. As scientists continue to study the mysteries of the universe, it is clear that every new discovery brings with it as many questions as answers. The complexity of cosmic phenomena, such as the ancient star HD 14283 and the age of the universe, challenges our current scientific models and forces us to reconsider the very foundations of cosmology. Each discovery opens the door to new theories and interpretations, prompting researchers to revisit their long-held beliefs and assumptions. A particularly intriguing aspect of these recent findings is the potential for a significant revision in our understanding of the timeline of the universe. If the age of the universe is indeed closer to 26.7 billion years, as suggested by Professor Gupta, it would mean that our previous calculations were too conservative. This new estimate, though controversial, could have profound implications, not just for cosmology, but for other branches of science as well. It may offer answers to fundamental questions about the universe's origin, the nature of dark matter, and the forces that drive cosmic expansion. One key factor in the ongoing debate is the concept of dark matter, which is thought to account for a substantial portion of the mass of the universe. Dark matter is invisible and interacts with regular matter only through gravity, making it exceedingly difficult to detect. However, its presence can be inferred from its gravitational effects on visible matter, such as the rotation of galaxies. The idea that dark matter might be less abundant than previously thought could explain some of the anomalies we observe, such as the slower-than-expected movement of stars in the outer regions of our galaxy. The Gaia satellite's data, which provide detailed measurements of the positions and motions of billions of stars in our galaxy, has led to a reevaluation of the mass of the Milky Way. This new assessment, which estimates the galaxy's mass at about 200,000 billion times the mass of the Sun, challenges earlier models that placed the Milky Way's mass much higher. If dark matter is less abundant than scientists have assumed, this would force a significant revision of our understanding of galactic structure. However, the process of measuring the mass of a galaxy is fraught with uncertainties, and scientists are cautious in drawing conclusions from these new findings. In addition to these intriguing revelations, there are also broader philosophical questions at play. As we learn more about the universe, we are constantly confronted with the limits of human knowledge and the need to remain humble in the face of the unknown. The pursuit of scientific understanding is not just about finding definitive answers. It is about asking the right questions and embracing the uncertainty that drives discovery. With each new breakthrough, we are reminded of how much there is still to learn and how much more there is to explore.